I'm about to finish with the abstract stuff, but you have to bear the abstract stuff for about another 20 minutes or half hour, then we switch to concrete applications. So where do we stand? Just to repeat, where do we stand at the moment? At the moment, we have a probability space, a Markov process, eta t, in omega, which is ergodic. We have the Hilbert space, which is L2 of omega pi. We have the semigroup acting on this Hilbert space. I denoted by PT, remember what it was. And its infinitesimal generator, which was, I just write formally like this, that means that this L was the infinitesimal generator. The infinitesimal generator was written in separated the symmetric or self-adjoint and skew self-adjoint part of it. So I wrote L as minus S plus A, where S stands for symmetric, A for anti-symmetric, and S is self-adjoint operator. S is a self-adjoint operator. I put here a minus sign so that this S becomes a positive semi-definite operator. Actually, yes, a positive semi-definite operator. And A is Q self-adjoint. A star is minus A. This is just a standard separation of operators into self-adjoint and skew self-adjoint part. I just repeat very fast what I was doing yesterday. We have a function, sometimes I call it phi, sometimes f. Let me call it phi in H with zero mean. With zero mean, and we are interested in Martingale approximation. In Martingale approximation, so Martingale approximation of integral from 0 to t of integral from 0 to t phi eta s ds. So integrate the values of phi along the trajectory. And the point is to find a martingale on the same filtration, on the same probability space where, so living on the same probability space where the Markov process lives, and adapt it to the same filtration. So Martingale approximation is such that this minus mt is small enough. By this I mean, you remember what I mean, I don't want to waste time. That means that I am informal. I write small o of square root of t, and by this I mean that the difference divided by square root of t converges in L2 to 0, right? In L2, small of t. So this is the good Martingale approximations we want. Once we have this one, due to the Martingale central limit theorem, in particular, we have a central limit theorem for this thing. We will see how to apply it, but this is our goal, yes? And so far, I have proved there was a number of things I've done, but the conclusion at the end of yesterday's lecture, the conclusion was the following, that holds, it's okay if the following two conditions hold. Okay, I should have written on this board one more thing. Call u lambda be r lambda f. R lambda is the resolvent, so I should put here somewhere. R lambda is lambda identity plus L minus L, minus L inverted. Or some other definitions were there. Anyway, this is a bounded operator, no problem with it. It's not the case that you can compute it explicitly, but it's a bounded operator. Its norm is bounded above by 1 over lambda. As long as lambda is positive, this is a bounded operator. And this is okay if the following two conditions hold. The first condition I called A was that square root of lambda, norm of u lambda, converges to 0. And the second condition was that this was a bit, and I'm afraid that I lost some of my audience because I wrote it this way, s to the 1/2 u lambda, and what I mean is the following. S is a self-adjoint operator. We have the spectral theorem. For unbounded operators, there is spectral theorem. The spectral theorem says that given a function, say a continuous function on the spectrum of S, you can define that function of the operator, and there is a formula. So it exists. If this was unbounded, that will be an unbounded operator, but a self-adjoint positive semi-definite unbounded operator, well-defined due to abstract function analysis, so that this converges. By convergence, I mean as lambda goes to 0. And this converges to some element of H. So this is a Cauchy sequence. This is a Cauchy sequence or a convergence sequence in the Hilbert space. And since this s to the -1, s to the 1/2 probably makes many of you a bit dizzy and you don't like it, because you don't like, you may like it, but the one next to you may not. The spectral theorem, I tell you what this means, to just come down to earth a little bit, right? This means the following. So this sequence must be Cauchy as lambda goes to 0. This sequence must be Cauchy in the Hilbert space as lambda goes to 0. This means the following, that the norm of S1/2 applied to u lambda minus u mu as lambda and mu goes to 0. I write down the Cauchy condition now, right? This must go to 0 as lambda and mu goes to 0, right? I make it squared. This must go to 0 as mu goes to 0. This is what? This is S1/2 u lambda minus mu scalar product with itself. S1/2 u lambda minus u mu. Right? It's the same thing. By self-adjointness, shift this thing on the other side, and you get u lambda minus u mu s applied to u lambda minus u mu, and we are done. This must go to 0 by the Cauchy condition. The Cauchy condition says that if lambda and mu go to 0 independently separately, then that must go to 0, right? But this is nothing else but u lambda minus u mu. Here I put L, u lambda minus u mu. Why? Because L is S plus A. These are the same. These are diagonal matrix elements. So A the diagonal between the same vectors will by skew self-adjointness will be 0, right? And we are in a real Hilbert space, right? So this goes to 0 as lambda and mu go to 0 independently. So that is the condition. Just to come down, because this s to the this is very handy, and we will use this formula. But actually, the meaning is this one. That this goes to 0. But by the way, so it's okay if these two conditions are, but these two conditions are difficult to check. In the self-adjoint case, there is a way to check it, because it's about checking a norm. Anyway, it's in the self-adjoint case, it can be checked. In the non-self-adjoint case, these are nice. It's a nice abstract theorem, which is very difficult to apply directly. So I'm going to tell you, this is sort of necessary. I don't claim strictly mathematically that this is if and only if for the central limit theorem, but is about if and only if. Right? You can't hope for much better than that. Now I will give you sufficient conditions, truly sufficient, which are far from this, but nevertheless are checkable and in particular cases applicable and good. The first one is what today we call it the strong sector condition, and this is due to Varadhan 1990 something, 97. I think, I'm not sure about the dates, but about those years, 95, 97, something like that. And he says the following, that if the following two hold, so the strong sector condition is the following for the operator, is the following, that for any phi and psi in the Hilbert space, phi a psi squared be bounded above. Okay, better I write it in a separate row because this is a short blackboard. Phi a psi squared be bounded by a constant. Okay, I should have said there exists a constant. There exists a finite constant such that for any two vectors, this is bounded by phi s phi times psi s psi. So in this sense, the self-adjoint, the anti-self-adjoint part of the skew self-adjoint part of the infinitesimal generator is dominated by, and maybe I'm confused with these because phi and psi, I use now phi and psi for general, for a typical and general element, and this is my particular f for which I want, if there is a particular f for which I want to prove the central limit theorem, and this is a general condition on the operator. This is not a condition on my function. This is a condition on the operator, right? And Varadhan proves that I put here the theorem due to Varadhan, 90. Check it in my lecture notes. I remember 97, it might be 95. Is the following, that if the strong sector condition holds and f is in H minus 1, remember H minus 1 was the range of S1, S to the 1/2, or the domain of S to the minus 1/2. H minus 1, just to recall, I write here H minus 1 is the space of those phis in H for which limit as lambda goes down to 0 of phi identity, lambda identity plus S inverse phi, this limit stays finite. And if you take this limit, it stays finite. This you can easily check. This is exactly those vectors, that subspace, on which S to the minus 1/2, the operator S to the minus 1/2 is defined. Mind, here comes in, this is, let me emphasize, unboundedness of operators, sometimes they just cause nuisance. You have to care about domains and about that, and in many cases it's just a nuisance. It's not essential. But this unboundedness is absolutely essential because it's related to the fact that you don't have a gap in the spectrum. If you had a gap in the spectrum, this would be a bounded operator, the inverse. You would be, the point is exactly, so this unboundedness of S to the minus 1 is an essential problem of ours. Is a core, it's at the heart of our problem. The other unboundedness, for example, that the operator S and L are unbounded, cause nuisance but are not important. So important. Okay, so this is the theorem of Varadhan. I'm not going to prove it now because I will prove another one which includes this one. And but this is very essential. And I tell you, where is it used? So where is it applied? Applied for, this is already applicable in many cases. Question? I'm sorry?
What's the conclusion of the theorem?
Oh, I'm sorry. The conclusion is okay. Then okay. If that implies okay. Is that fine now? Then these two hold. right? That's the conclusion of the theorem. Thanks. Very important. Okay, now, applied. Where is it applied? First of all, Varadhan invented it in order to prove central limit theorem for tagged particle in zero mean but not symmetric simple exclusion. So tagged particle diffusion in zero mean but I always mean finite range. All my walks will be finite range. I don't want to cause headache with infinite range. Finite range, zero mean, exclusion process, simple exclusion process. You remember what the model was, that particles try to jump independently, but they are not allowed to jump on the top of each other. Now the jump kernel is not symmetric, because that would lead to self-adjoint problem. The jump kernel is not symmetric, but is zero mean. Now what Varadhan proves that in that case, with a very, very clever decomposition, I don't have time to show you now, it's very, very beautiful. Go to see this paper of Varadhan, and you will see how ingenious it is. He proves that, he doesn't exactly uses this, there are many other formulations, but he proves that in that case, this type of boundedness holds, and from this type of boundedness, which is simply called sector condition, because later another sector condition came, which I will show you, and that's why I call it strong sector condition. And this implies the Martingale approximation. The logic of the essential is the same. It doesn't use exactly the same steps as I did it yesterday. Mine is a bit more streamlined, maybe, that the idea is there. So that's one of the conditions. No, I wanted to give you more examples. This is one example, and here is another example which is already close to my application or part of my application. Take random walk in divergence-free or doubly stochastic random environment, as I defined it already, yes, but of a particular type, generated by finite, so how do they call it, with finite cycle decomposition. I tell you in a moment what it means. It will be a particular case of what I show you later today. With finite cycle decomposition. And I gave you an example yesterday, a day before yesterday, this example with the small cycles around the blocks. That was a very simple. So there were two types of cycles, one on a plaquette going this way, the other one on a plaquette going that way, and I placed randomly these cycles in a translation invariant ergodic way. I placed randomly these cycles on the lattice, and I defined the random walk in terms of these cycles. Now imagine that you have finitely many different cycle types, not only these ones, but you could have this cycle and another one, but you have only finitely many of these. You give some weight to these and form a Poisson point process, a cloud of these cycles on the lattice, and define a random walk in terms of those. Right? Now if you do that, then we'll see later the strong sector condition applies. And this was proved in many different disguises, actually, in the last, say, 20 years by many people. The first one named to mention here was Kozlov, M.S. Kozlov, back in the 80s, 85. He didn't speak exactly in these terms. He claimed a bit more or quite more than what he actually proved. He's a great mathematician, no question about that, but that particular paper is a very rich in ideas paper, but sometimes not totally, not all steps are fully rigorous. But anyway, this particular case, or some sub-case of this case is done there in that paper. Later, okay, I will not mention all names because I'm not able to do. I'm sure that, that a paper by Komorowski and Olla is about this. In the 2000s, where they do that, and they do an yield, so a subcase of what I'm going to do later today. There is a quenched result for this type of work by Deutschel and Kösters. I should write it, I just say the name, Deutschel and Kösters. So this is considered by many. And it's non-trivial. Not all people apply this. They might apply other, for example, Deutschel and Kösters don't apply this type of approach. But this approach works, and then my first example is just one of the simplest of these. Clear? Okay, a next condition, a next sector condition, which came with this is a bit more complicated, and I might, but I want to use it later next week, so that's why I state it now. The so-called graded sector condition. Sector condition. The graded sector condition, and this is due to Seturaman, Varadan, and Yao in I think it's 2000. I'm not totally sure about the dates, but I think the paper was published in 2000. Now this is technically complex. If it happens that there is a natural grading of your Hilbert space, though some of you may have, I'm sure some of you are well trained in chaos decompositions. Hands up those who know chaos decompositions. Wiener chaos. Not so many. Fock space, which is the same. Okay, some say no Fock space, but actually it's the same as Wiener chaos, isn't it? Anyway, so if you have a Gaussian Hilbert space defined, a probability space spanned by a Gaussian, defined by Gaussian random variables, for example, by just one Gaussian, then L2 over one Gaussian can be decomposed to infinite sum of one-dimensional subspaces. These are the Hermite polynomials, aren't they? Hermite polynomials of a Gaussian are orthonormal, right? Now you may have more than that. Anyway, in some particular cases, H can be written down as an orthogonal sum of subspaces H sub n. And those who know Wiener chaos think about this as the Wiener chaos decomposition. Those who know Fock space think about this as the Fock space decomposition. Those who don't know these two think about it, say that your probability space is defined by one single Gaussian random variable. And the L2 space is spanned by the Hermite polynomials. Right? And the Hermite polynomials define but in that particular, all these H sub n's will be one-dimensional. But yeah, if you have a multivariate Gaussian, maybe that's the good example. Your Hilbert space is L2 over a multivariate, so your probability space is spanned by a multivariate Gaussian, by Gaussian field, which could be finitely many Gaussians or infinitely many joint Gaussians. Take H naught will be the constant, H1 will be the linear span of the Gaussians, so all Gaussians, H2 will be the linear span of all second order Hermite polynomials of all these guys, and so on and so on. And these are all orthonormal spaces. It's Gram-Schmidt orthogonalization. So if it happens that your Hilbert spaces are, of course, all Hilbert spaces are the same as we learned in abstract function analysis, so far I didn't say anything. But it's naturally linked to your Markov chain in the sense that, say, S maps Hn to Hn. I simplify a little, I don't give you the most general form of the theorem. That means the symmetric part keeps the grading, and the skew symmetric part only mixes finitely many. So let's say I put here an Sn to say that Sn maps Hn to Hn, and that's all you have. So S doesn't mix the spaces. It's block diagonal in this orthogonal decomposition. And H sub n M maps HM to HN for n minus m less than some r. So if you write your operators in block diagonal form according to this orthogonal decomposition of the Hilbert space, then you have on the diagonal you have the symmetric ones, and on the off diagonal, but only up to finitely many, you have the asymmetric part acting. This is a very special thing, but in many cases, and in one of my main applications, it will be the case. Right? And assume, and now I write down the graded sector condition. The graded sector condition is the following. That for any, say, phi in Hn and psi in Hm, now let me see, A and M psi phi, and this is scalar product in Hn. Yes, because this is you could push this on the other side. Of course, A star of Mn is minus A of Nm. That's easy to see, right? So this squared is dominated, and now this is complicated a little. Again, I should say, maybe I follow my notes because I will make mistake otherwise. Give me a second. Yes. There is a constant, an absolute constant, so it's less than c squared. Probably I should have put c squared there too. I have delta nm, so on the diagonal you must have a bound of whatever order. Kappa is whatever power of n to the kappa is whatever power of, so kappa is just a finite number. Plus, if you are off diagonal, then this must be n to the beta, and with the following times, I forgot to write times, I have psi s mm psi, and that is squared, yes, and phi sn phi. It looks like crazy. I didn't say what the c is a general constant less than kappa is whatever finite, and beta must be less than 1. That's very important. Beta must be less than 1. So what does this say? It says that, okay, this is graded, so altogether there is no condition like this. But on the grades, grade-wise, you have with worse and worse constants, because this can increase with n, but not too fast. Right? Now, this looks like a terribly technical thing, and the proof, if you look at the original proof, it's indeed terribly technical. But it's very important because it helps you prove that this condition A and B before hold in particular cases. This was applied by, in that paper by Seturaman and others, it was applied to the original application was to tagged particle, tagged diffusion in general simple exclusion without any condition. Simple exclusion process in dimension more than 3 and more. So take a general simple exclusion process, no restriction on the jump rates, except that they are finite range and homogeneous, right? The central limit theorem will hold to the tagged particle diffusion. In this case, you might have to subtract the mean, right? and the central limit theorem will hold in 3 and more dimensions, and the proof goes through this. I don't give you this is a very, very technical and difficult and very important result. But I will apply to the self-repelling Brownian polymer. Remember, the self-repelling Brownian polymer was a Brownian motion, essentially wants to be a Brownian motion, but it's pushed by the negative gradient of its own local time, of its own occupation time measure. In 1 and 2 dimensions, it's super diffusive. In 3 and more dimensions, it is diffusive, and the central limit theorem is proved by a long story and some sort of extension of this. Right? Now, before going on to a third theorem, which is my theorem I want to tell you, is the following. Before going on, I want to show you the following. This condition is equivalent, this is a strong sector condition, is equivalent to saying that A s to the minus 1/2 s to the minus 1/2 as an operator, if I write down this operator, a priori doesn't make any sense. A priori doesn't make any sense because this is an unbounded operator. You have to specify where you act, right? Because you act, it's defined only densely. Say this guy is bounded, not to complicate our life. This is unbounded, take a vector from its range, from its domain, get here, this is a bounded, get here, somehow you might be lost fully. It may happen that you can't apply this one anymore. But this condition is equivalent to saying that this operator a priori is densely defined and actually it is bounded as an operator. Let me put here a c squared, and this condition is equivalent that this operator can be defined as an operator has a norm less than 1, less than c. So just I want to go towards my formulation of the sector condition where this type of formula will appear. So this is the operator type of condition here. And if we go to the sector condition, I don't want to write down this term again, so I just replace altogether. This condition is equivalent to saying that the norm of this operator, maybe this beta is 2, not 1. Beta by 2 must be, I don't remember now, either 1 or 2. Anyway, a finite number. That the operator norm of Sn to the minus 1/2 ANM Sm to the minus 1/2. Now let's see whether it makes sense or not. This formally, you start in the Hilbert's, in the subspace H sub m, leave you in H sub m, this takes you H sub n, and this leaves you in H sub n, right? So this operator a priori, again, I should repeat, a priori may make no sense, but the condition written here means that the operator norm of this guy is bounded by c times probably that. Right? So it says that this operator, which a priori, mind that this is altogether this operator will not be bounded, because as you go upper to the grades, you get worse and worse bounds. But grade-wise is bounded. Okay, so these are the theorems which came from Varadan and others. And when I started to work on some problems related to this, some about 10 years ago, I realized that this type of operator, which is scary because indeed it doesn't make sense. So you have to be very careful about how to define it. This plays a key role. And let's see what is the key role of this operator. And let's go to what I call relaxed, maybe the name is not so good, relaxed sector condition, relaxed sector condition. And what I'm going to tell you is based on a paper of some students of mine, that's Horváth myself and Vettel, published in 2012 in a celebrating volume, an issue of a journal celebrating Varadan's 70th birthday. Anyway, so let's do the following. Let me define the operator B lambda. I will be a bit careless about domains for the moment because I want to give you the big picture. I see that you follow very well what domains. You are in functional analysis somehow, aren't you? Yeah, good. It's very clear. I can see on the eyes of people. So just just trust me that I don't make big mistakes with domains. Good. So I define B sub lambda as the following operator: lambda identity plus S to the minus 1/2 A lambda identity plus S to the minus 1/2. Let's assume that A is a bounded operator, that the infinitesimal generator is bounded. That I told you that there are unboundednesses which are just nuisance and unboundednesses which are essential. Now A might be unbounded, but that's just the nuisance part. The essential thing is the unboundedness of S inverse or S minus 1/2. Good? So assume A is a bounded operator, then this is a well-defined bounded operator. Why? Because this is a strictly positive operator, inverted or square root inverted. This is a bounded operator. The norm of this operator is bounded above by lambda times norm of A. This is a bounded operator, well, and it's a skew self-adjoint. Do you want to ask something? I'm sorry, I don't.
It's the square is lambda I plus S.
Plus S.
Yeah. So it's a positive.
Is a positive operator.
Norm should be greater or equal to lambda, and then you take the.
No, it's not that its norm is greater than lambda. The lower end of the spectrum is greater than lambda. So its inverse will be bounded by lambda, in norm. So the norm of this guy. Norm of lambda identity plus S to the minus 1/2. It's to the minus 1/2. By spectral theory, I take this is a self-adjoint operator. It's a positive self-adjoint operator. It has a square root operator. It has a negative square root operator. By spectral theory, the norm of this guy will be less than lambda to the minus 1/2. You agree?
Yes.
Good.
So it should be bounded by something times 1 over lambda.
That's what I didn't I say that?
You said it should be something times lambda.
Oh, sorry. No. I meant 1 over lambda, of course. Sorry. Okay. So that's the point. This is bounded. This operator norm is bounded by norm of A times inverse lambda, or 1 over lambda. Yeah. Sorry. Then I'm sorry. So I made a mistake. Okay. So I define this operator B lambda, and I define the operator. This is, and mind that this is very important. B lambda star is minus B lambda because these are self-adjoint and this is skew self-adjoint. Then I define K sub lambda. The following operator is K sub lambda, is identity plus B lambda inverse. Identity plus B lambda inverse, mind, B lambda is a skew self-adjoint operator, its spectrum is imaginary, so identity plus it is invertible and its norm is actually norm less than 1, norm at most 1. So K lambda, norm of K lambda is less than or equal, actually equal to 1. Why? Because this is invert 1 plus an imaginary number. 1 plus imaginary, absolute value of 1 over 1 plus imaginary is less than 1. Right? Good. And why did I do that? Because I write the resolvent, and this is just an identity, the resolvent, the resolvent was, I just recall, plus L, plus, say, S plus A, minus S. Plus S minus A, like that, yes, inverse. This is just definition. But with this K-sub-L, it is written like lambda identity. It's written like lambda identity plus S to the minus 1/2 K sub lambda, lambda identity plus S minus 1/2. You must agree it's an element, it's manipulation with symbols. It's nothing deep there. Right? And everything I write down so far, I will not cheat. These are all bounded operators. All operators you see and inverses you see at the blackboard, on the blackboard are bounded operators. No cheating. Good? Okay. Now, if by some miracle, if by some heavenly miracle, if by some heavenly miracle it happens that K sub lambda, no matter how you play with the lambda, K sub lambda stays finite, stays bounded. K sub lambda converges in the strong operator, let me say stop, for the strong operator topology. Anybody does not remember what the strong operator topology was? Hands up. Oh, first I finish and I write down. So when you are in Hilbert space and in operators in Hilbert space, you have to be very careful about what you mean by convergence. You have norm convergence. Everybody knows what norm convergence means. The norm of the difference of the limit operator and the operator converges to zero. The norm of operator norm. That's too strong. Don't expect. What we call strong operator topology is weaker than that, but stronger than something what we call weak operator topology. So the strong operator topology means pointwise convergence, means that for any fixed phi in the Hilbert space, K lambda phi converges to K phi. So it's not a norm. You don't take supremum over all of the difference of the norm of the difference over all vectors of norm 1, but pointwise. For any fixed element of the Hilbert space, you have in finite dimension, of course, all these convergences are the same, but we are not there. Good. So if by some miracle this happens, then I claim that, and I will show you, then take f from h minus 1, then for f from h minus 1, A and B holds. I mean okay. When I say okay, I mean that the conditions of the Kipnis-Faraday, of the generalized Kipnis-Faraday theorem hold. And this is what I'm going to show you. Before I do that, I want to emphasize something I should have done before. When I spoke about the graded and the strong sector conditions, there were always two conditions. One about the operator, one about the function. The strong sector condition and the graded sector condition was about the operators. And beside that, I had the condition for the function being in h minus 1. Right? So these are the, again, I have a condition of the, okay, you will see what this means. You will see later. Now I just said if by some miracle this happens, I tell you when it happens. That will be a condition on the operators plus a condition on the function to be integrated, be in h minus 1, and the two together imply what we need. Right? And let's see why. Mind that this means that f is equal s to the 1/2 g, with g from h. Good. Let's prove this, and we see and hope for the miracle. This is a simple, once you know what the meaning of these things are, my condition A was the following. I had square root of lambda times u lambda to converge to 0 as lambda goes to 0. And let me again emphasize, if I didn't have here the square root, then it would be generally true. So for a very, very wide context, in very wide context. So the point is that here I don't have lambda u lambda, I have square root of lambda u lambda, which is much bigger. Right? Let's see what we get. We get lambda to the 1/2. We get lambda to the 1/2, it's there. U lambda is R lambda applied to F. U lambda is R lambda applied to F. R lambda is here. Lambda identity plus S to the minus 1/2. I have K lambda. I have lambda identity plus S to the minus 1/2. And note that F is given as S to the 1/2 G. S to the 1/2 G. Now, by the spectral theorem, these are self-adjoint expressions. These are self-adjoint operators, or functions of self-adjoint operators. S is positive, and mind, S doesn't have zero eigenvalue. So I pushed away the zero eigenvalue. I said that H, I told you from the beginning that I will be a bit loose about this. So H is, I'm restricted to the subspace of one codimension, where S is, doesn't have the zero eigenvalue, right? Now, by the spectral theorem, you easily see that this converges strongly to where? To what? To identity on, or projection, actually projection to the zero mean subspace. Why? Because the function, think about this as a function, as just a real a positive variable. You have S divided by square root of S divided by lambda plus S. When lambda goes to 0, this function converges pointwise to 1, right? Except at S equals 0. And apply the spectral theorem. Okay, just trust me if you don't remember what the spectral theorem was. This converges to identity, right? And for the same reason, this converges strongly. By stop, I mean strong operator topology. To what? You have lambda, square root of lambda divided by square root of lambda plus S. To what function it converges pointwise when lambda goes to 0? S is positive. Pointwise, I have the function lambda by lambda plus S on the positive semi-axis. I mean, S is on the positive semi-axis. Pointwise converges to square root, say, 0. So this converges in the strong operator topology to the 0 operator. So, and now take your vague memories of elementary function analysis. You have a fixed vector. You have a sequence of operators converging strongly to identity. You have a bounded or uniformly bounded operator. This is a uniformly bounded a sequence of uniformly bounded. It's very important that these K's have bound 1. And this guy converges strongly to 0. This will converge to 0 as it is. So we have condition A. Let's go for condition B now. By the way, I used that K sub lambda converges strongly. I didn't write it. K sub lambda converges strongly to K. That's what I should have written here. So all three components converge strongly. This to a bounded, this one to a bounded, and this one to 0. Then the product converges strongly to 0, and we are done with that. Now let's go to B. I have to prove that S to the 1/2 U lambda converges in the Hilbert space. And I have something very, very similar. I have S to the 1/2. I have R lambda. This is R lambda F. I have R lambda, which is lambda plus S to the minus 1/2 K lambda, lambda plus S to the minus 1/2 S to the 1/2 G. And again, this converges strongly to identity. This converges strongly to identity. What did I write here? Anyway, to identity, and this converges strongly to K. and using all what you know about strong operator topology, you find that this converges strongly all together to K times G, which is an element of the Hilbert space because K was supposed to be the strong operator limit of K, which is a bounded operator. And we are done. Okay, we are done assuming this miracle. Assuming this miracle. Now let's see what that miracle means. So, okay, let's conclude that indeed if the miracle happens, then we are done. Now let's see what the miracle means. So the miracle is the following. I want to prove, I write down what was K sub lambda. K sub lambda was identity, 1 over, so inverse of identity plus B lambda to the minus 1. That was K lambda. And B lambda, just to recall, B lambda was S lambda plus S to the minus 1/2 A lambda plus S to the minus 1/2. Right? As long as lambda is finite, positive, there is no problem here. These are well-defined, bounded, and so on, as we have seen. What happens when lambda goes to 0? Now, the problem is the following. Let's be formal. Let's be formal. Think about everything between quotes now, because it may not make sense, but it will make sense. As lambda goes to 0, in some way you expect that in some way, which you have to be very careful about, you expect that this will converge to an operator, which is what? Lambda goes to 0, S to the minus 1/2 A, S to the minus 1/2. We have seen it before. But let's put it between quotes because this doesn't make any sense. Because as long as lambda is positive, it's okay, but when lambda is 0, you don't know what this means. Right? Now, I tell you what is the point. What you have to prove is the following. And now, please put your attention here, because even for those who don't know, who are unaware with unbounded operators and all that, will appreciate, I hope, the importance here. You want, if I was able to give sense to this operator as an unbounded but skew self-adjoint operator. So that means I want to make sense of this thing. I want to find a dense subspace. I want to find, so the goal, find a dense core, say C, a dense subspace. Right? On which you can define B, on which B is defined. Is defined. In general, it's not. Find a good and that's the concrete problem we'll tell you. This is abstract now. It's a concrete problem. We go to the concrete problem and see. Find a dense subspace on which is defined. Automatically, it will be skew symmetric. It will be the case that for phi and psi in C, it is the case that phi B psi equals minus B phi psi. Why? Because these are self-adjoint. I chose a set of functions on which the things make sense. Right? Say C set of functions so that if you start from here, this is defined, here you land in the domain of S to the minus 1. Say that exists. There are densely there functions for which this happens. That's not difficult. Now, if this happens, you easily check that the operator B defined on this dense subspace will be skew symmetric. And now go back to your class in functional analysis. B is an unbounded operator, densely defined, which is skew symmetric. It's not symmetric. For symmetric, I could say the same words, just a minus somewhere or an I somewhere. It's not the case that this is skew self-adjoint. A symmetric, densely defined symmetric operator is not a self-adjoint operator, necessarily. You have to struggle for it to prove that it is self-adjoint, that its closure, you have to close the operator, take the graph of the operator defined on this subspace, close it, it's closable due to the skew symmetry, and skew symmetry, it's closable. That means that the closure of the graph will be a graph of an operator. But it may happen that the adjoint is not coinciding with the closure, but with the negative closure. It may happen in unbound. That's the deep problem of constructive quantum physics, for example, that you define operators with in kitchen terms, and you have to prove that these operators do make sense as unbounded operators. That means that they are self-adjoint. So what I have to prove, and the theorem which I'm not going to prove all because it's very, very technical, and not very many of you are disappointed, but it's there in the notes. But I don't want to waste much time. But the point is the following. If I'm able to prove that this operator, densely defined, is closable, its closure, it's skew self-adjoint, which is something to be proved, then I'm done. Then I'm done. So vaguely, the theory, you find a very, very rigorous formulation in the lecture, in the handwritten part of the lecture notes, and the full proof there. So it's nothing fishy here, what I'm saying. Just the proof is indeed sort of, maybe tour de force is too much to say, but it's function analysis, abstract function analysis. It's not so instructive to make it in front of 100 students, right? The point is the following: the goal, prove that B defined on CH is essentially skew self-adjoint, so that its closure is skew self-adjoint. So the closure of B is equal to minus D. Right? And there is a way to do that. This is von Neumann's criterion, and this is the last word in function analysis I tell you now. Von Neumann's criterion for self-adjointness that translated to skew self-adjointness. Von Neumann was interested in how to prove that the Hamiltonian for a quantum system which the physicists give you is indeed makes sense as a mathematical object, that it's a self-adjoint operator, right? And that's how the problem came. This is not a quantum problem, but it's very similar, right? Now, von Neumann's criterion is the following. Given a skew symmetric operator, you can easily define its adjoint. The adjoint of unbounded operators are defined in a way which I'm not repeating now. It makes sense to speak about the adjoint of a bounded operator. So take B star, the adjoint of B. I can give you the definition if you wish, but it's a very natural one. B star, you have to, okay, let me not waste time with that. At the concrete example anyway, I will go through this. At the concrete example, I will go through this, all steps, and you will see how we apply it. So you have B defined there, take B star, and von Neumann says the following: you must prove that B star plus identity doesn't have zero eigenvalue. Plus and minus implies phi equals 0. Separately, not the two together, either one implies implies phi equals 0. So mind, B star will be extension of B. B star will be extension of minus B, so will be bigger. So it's not enough to prove it for phi's taken from the domain on which you define B. That's the difficulty. That's easy. If you take a phi from this C, then from this formula you can easily see that it cannot happen. But the point is that you have to check this for all phi's in the domain of B star, which is a huger extension. Right? And this is the point which we'll check in our concrete application. Right? So the theorem, I don't even state the theorem now because it's wasting. You find it in the lecture notes. But the conclusion, the morale of the theorem is that if we are able to prove about this operator, which is defined a priori only as a dream, but if you can take it down to earth and show that it's a well-defined object as a skew self-adjoint operator, not just skew symmetric, but skew self-adjoint operator, then we are done. Then all things follow. And let me just add that this is better than the previous ones. So the previous ones, the Varadhan type of theorems, are consequence of this one. There are stronger conditions than these. Right? And now I'm ready with the abstract part. And I don't know how much time. I simply don't know when do I have to finish. 30 minutes, good. And then, yeah, question?
So lately you will give concrete examples of A and S to which the scheme works, right?
Yeah. So I will go with very concrete examples.
And previous don't. So conditions of Varadhan not, but this one.
Exactly. So that's why I worked on it, because the Varadhan conditions for the random walk problem I'm going to from now on to speak about, neither of the Varadhan conditions work. Right. So the graded works only when you have grading, when you have a natural grading of the space, which is consistent with the action of the operators, which happens very rarely. It happens in Gaussian cases, when the space is Gaussian because you have a natural grading and possibly also your operator is observing that grading in a sense. When you have the interacting particle systems problem and Bernoulli measures, then the grading works because you have something similar to Fock decomposition. But not in other cases. For this simple-looking problem of random walking random environment I'm going to speak about, you don't have either of them. But you will see. Now I start speaking about the concrete. I apologize for this long abstract digression, but these will be the theorems used. And this is a type of story which doesn't go without this function analysis type of thing. But I want to emphasize that what we are doing, so it becomes interesting only because it has very concrete down-to-earth applications. So an abstract theory would be worth nothing. Good? Okay, so now I go to the random walking random environment, a particular random walking random environment problem, namely the bistochastic random walking random environment. So I have a probability space, but not only a probability space, but I also have an ergodic action on it, tau z in zd. Okay, let me write it like this. Tau z maps omega to omega for z in zd, right? And this is an ergodic dynamical system. Everybody understands what I mean, right? I have a probability space and the ZD action on it, which acts ergodically. Ergodic means that any event in omega which is invariant to all translations must be either of measure 1 or of measure 0. Good. And we'll speak about nearest neighbor walk, so I just call this script E the possible steps of my walk. So it only steps on nearest neighbors. The random walk will live on ZD, right? And I have jump rates P sub k which map omega to R plus, and these are jump rates. These are jump rates. I will assume about the jump. So assumption one is bistochasticity. No, first I write down the random walk. The random walk is xt, t maps to xt in zd, such that the transition probability is, given omega, the transition probability, the probability that xt plus dt is x plus k conditionally on xt was at x, be p sub k tau x omega dt. So this is just a fancy way of writing that I have a stationary, on ZD, a stationary sequence of jump rates, of random jump rates. Right? Sometimes I will use this notation. I will denote this sometimes as p sub kx without denoting the omega, because this is the jump rate from x to x plus k, from x to in the k direction. Right? So this is the general, this is just a random walk in random environment. All random walks in random environments are here. Random walk in random environment is this. Right? Now my assumption is assume bistochasticity. Assume bistochasticity. Bistochasticity is the following. The sum of the rates going out are equal to the sum of the rates coming in. P minus k omega. And if you lift it like that, this is true for any translation. So if you translate it with x, then you get at each single point of the lattice, the rates of jumping, the sum of the rates jumping out equal the sum of the rates jumping in. Right? This is double stochasticity. Now, why is double stochasticity a natural condition? By the way, the random conductance model is included here. Namely, you will see later what the random conductance model is. So this is much more than the random than the self-adjoint. It's not self-adjoint, right? Now, why do we love, or why do I like bistochasticity? There are many reasons to consider it. First reason, why? Why care? Why care? There are mathematical and physical reasons to care. The physical reason I told you already, that you will see later, not much later, in 2 minutes, in 5 minutes, that this condition corresponds to some sort of divergence freeness of the local drift. That the local drift of the walk is divergence free. It corresponds to that thing. And divergence free drift in physics language means incompressibility. So this sort of models random motion of a suspended particle in a divergence free drift field. That means turbulence. That means it's also random, so it's a random turbulence. So of course it's not describing from microscopic principles turbulence, but it's a mathematical model of drifting in turbulent flow. So that's the physics, why, that's the physical motivation why it's interesting, right? The mathematical motivation, so physics, divergence free, drift is the same as incompressibility and sort of models turbulent flow. Good. Mathematics, okay, there is an abstract version in mathematics, namely that we want to go beyond the self-adjoint cases to understand more what's not self-adjoint, but it's not very satisfactory. If you have a general random walk in random environment, we will look at, maybe I run a bit ahead, the process I will look at will be eta t be defined as tau xt omega. So this is the environment as seen from the random walker. Right? And this is, you easily convince yourself, this is a Markov process. This is a Markov process on this space with this stationary, okay, with this measure, which is, we'll see stationary, we'll see in a moment, it's stationary, and it's ergodic. So this will be our Markov process. Consider the environment seen by the random walker, right? Now let's, first of all, I want to understand whether it's stationary or not, right? And forget about this for a moment, because I wanted to give you as a motivation, but before, forget, for the moment, forget about that, right? Is homework for you, and it's an easy homework for you, the following. If I am trying to, I want to find rho omega such that rho times d pi is stationary for eta. Okay, so I just gave you, what did I do? I gave you a random, I gave you translation invariant ergodic something, I gave you jump rates, I defined a Markov chain, a Markov process. This is easy to see that this is a Markov process. You can write down its infinitesimal generator. I will do it later, right? And now I ask, is it stationary with respect to the measure pi? The pi was stationary in time. The pi was stationary with respect to spatial translations, and your jump rates are stationary. But is the random environment seen by the particle stationary in time or not? Now, if you write down the equation, the homework is the following. I write down the equation and you check that this is indeed the equation. You have to solve the following equation. You have to solve the following equation. Sum over k p rho tau k omega p minus k tau k omega equals sum over k rho omega pk omega. Rho k, oh yeah, pk omega, yeah. So this is the equation to be solved. The solution of this, if it exists, so this is the equation to be solved. Your homework is not to solve it. Your homework is to check that this is the equation to be solved, right? It's just backwards Kolmogorov or something you write down, right? Now, my first remark is that if this holds, then rho identically one solves it. Yeah? Then rho identically one solves it. If this holds, take rho identically 1, that equation is exactly this one. Sum over kp, okay, this is a minus here, maybe it doesn't, you don't see. It's the same, right? It's the same. So mathematically, these are exactly the random walks for which the distochasticity is exactly the if and only if condition for this pi to be a priori stationary. Otherwise, in order to get it stationary, you have to solve this equation and initialize your process according to that measure. Now, solving this equation is terribly difficult. There is no way of solving it. If you don't really know, in very particular cases, you can solve it. There is no way to solve it. So I wanted to get rid of this problem. Let's not care about the stationarity. Take that model which is stationary from start. On the other hand, I ran a little bit ahead to give more motivation. If it's not the case of bistochasticity, then assume you solve this equation and you define a new random walking random environment with these rates instead of the original ones, that will be bistochastic. So from this you conclude that the bistochastic random walking random environment is just a time change, a random time change of the most general random walking random environment. Take the most general random walking random environment, assume that the stationarity equation has a solution, which is an assumption, it's not always the case, right? Assume this equation has a solution, then by a time change, by random time change, as you learn in random change of time of Markov processes, you can transform it into a random walking bistochastic random environment. So if you understand well bistochastic random environments, then possibly you get information for the more general class. So that's the mathematical motivation. Okay, so I gave you sufficient motivation. Now let's go on. Let's go on. I will denote, I will separate the symmetric and skew symmetric part. I will write S sub k omega be 1/2 of p sub k omega plus p sub minus k tau k omega. And I will write v sub k omega equals 1/2 p sub k omega minus p sub minus k tau k omega. So I call the first one the symmetric component of the jump rate and the asymmetric and the skew symmetric component of the jump rate. Right, and of course, by definition, you clearly see that S sub k omega is equal to S sub minus k tau k omega. So it's defined on edges, and it's even on edges. So on the oriented edge, on the oriented and inverse oriented edges takes the same positive value. This is positive because it's sum of two positive things, right? And v sub k omega equals minus v sub minus k tau k omega. Right? Now what you see here, this is my central object. If v is 0, then we are in the case of we are in the symmetric case in random walk among random conductances. So if v is 0, if you have an extra symmetry, namely that which is equivalent to this thing, then it's random walk among random conductances, right? And okay, now what I want to say is the following. So a few notes about this. Now you can also raise everything. You can lift everything on the lattice. So you can say I can use let me use the notation skx be sk tau x omega and vkx because it's vk tau x omega. I hope it will not cause confusion that I sometimes interchange it. Just to understand what I mean here, I have the lattice, right? I have the lattice. This is the site x. This is the site x. This is the edge k pointing out, right? And this tells me that I have some numbers sitting on the oriented edges, right? I have some numbers sitting on the oriented edges. This number sitting on the oriented edges is the same on both orientations. And this number sitting on the oriented edges is skew, is opposite. This is what I call a flow. I'm not sure whether Asaf is around. Probably he is. Ah, yeah. Okay, so I call this a flow without the assumption of divergence freeness. I add as an extra condition. A flow is a set of numbers on oriented edges such that on the inverse oriented it's inverse, just that. Because this corresponds to a vector field in RD. This has the algebraic properties of a vector field in RD. right? But on the top of that, the bistochasticity is equivalent, if you look there, is equivalent to sum over k in E v sub k omega equals 0. So that's the divergence-free condition. That's why I said that it's divergence-free. This is exactly that. This tells me that lifted to the lattice, if you add the outgoing flows at each single site, they add to 0. So that's Asaf's definition of a flow. He adds the sourcelessness. I say sourceless or divergence-free flow. I call what Asaf calls a flow. Good? Okay, and this corresponds in continuum to divergence-free vector field. To divergence-free vector field. Now what I want to, let's go on. Okay, of course I'm interested on the random walk and on the central limit theorem for the random walk. And before going on, I will give more conditions. I give more conditions. I will assume, another assumption I make is that ellipticity. Ellipticity means the following, that S sub k omega for all k's is larger than or equal to than some lower bound which is strictly positive. So the symmetric part of the jump rates is bounded below by a positive number. That's what we call ellipticity. Right? I will sometimes assume that it's also upper bounded, but not always, so I will put it boundedness assumes Sk of omega is less than or equal to S upper star, which is the same as P. So here is a very fine difference. The upper boundedness of S is equivalent to saying upper boundedness of P. You easily check. But the lower boundedness of S doesn't imply lower boundedness of P. You can have, for example, in my Manhattan model or in my square ice model last time, P was 0 in always you had two directions on which P was 1/2, 1/2. And you couldn't go against the arrows. But if you take the symmetrized thing, that will be lower bounded. The jump rate from here to here plus jump rate from there to here is bounded below. Not the jump rate separately from here to there is bounded below. And this is an important difference. Anyway, so I assume the lower boundedness. Sometimes my most general theorem doesn't assume, but I don't think I can give you the most general form because it's simply too much. So this I put in parentheses because it's not essential in the whole thing. Some boundedness in integrability sense will be essential. So actually, okay, let me tell you that more generally, L2, namely that expected value of Sk squared be finite. This will be in the most general setup, this will be imposed. But I will not have time to speak about the most general setup. Okay. This is certainly much weaker than that. Anyway, let's assume boundedness for the moment of the rates. If the rates are bounded, then there is no difference between discrete time and continuous time. If the rates are bounded, then you can realize the continuous time as a discrete time random walk plus an exponential clock. Good. And what else do I assume? At the moment, I still assume something, zero mean. Zero mean would mean, you will see why, that the integral of these guys, integral of v sub k d pi is 0, and this will imply that my random walk altogether doesn't have a drift. And my question is, sorry. And the question is twofold. Is CLT for the walk, but in two different ways. I will speak about probability of an event, P omega of an event, means that you fix omega, sample omega from capital omega, which is raised now, but is given, and ask about what happens with fixed omega. Maybe you prove something almost surely with this, something for almost all omegas. This is the quenched setup. And I will also speak about P of some events, which is integral on omega, P omega d pi, and this is the annealed. Right? And my question is the central limit question for the random walk. Right? And there are two questions here, two possible questions. The quenched one, which is stronger, is it true that for almost all fixed omegas, the random walk obeys the central limit theorem, or a slightly weaker one, that is it true in averaging over the omega? So that's why I fixed it. And the answers will be yes in both cases, but under somewhat different conditions, but that will be the story for... It's about time to finish? 5 minutes left, good. 5 minutes left. I will have time in 5 minutes to give you the main assumption. Yeah, let me do the following. In order to keep notation simple, since I'm emphasizing the new stuff, so which is non-self-adjoint, which is more than just random walk among random conductances, let me assume, trust me that in the paper things are done with general S sub case, but let me assume for the rest of these lectures that S sub case are just fixed constant. And of course, then V sub case must be less than S plus V gives P, so S plus V is positive, so V cannot be minus. But the main difficulty comes from V, not from S. And the examples I gave you were like this. So for example, in the Manhattan and in the square ice example, if you had each edge was oriented in one of the two directions, the sum of the two gave the same number, right? All over was not number. So there are interesting examples. There is no cheating here. Maybe, okay, give me this liberty. Give me this liberty to decide that I make simplified. There are some interesting things, but time is finite. And okay, now, no, I don't erase this yet. I don't erase this yet. Yes, I will make this assumption, and I just will make comments that there are some other issues arising at some points, but I make these assumptions from now on because otherwise we waste a lot of time. Now, the drift, so the conditional expectation of x t plus dt, okay, let me write dxt, given xt, expectation with fixed omega quenched, equals x, you easily compute. So there was the rates were here, you don't see anymore the rates, you add the step vectors weighted by the rates. So this will be, you easily see sum over k times v sub k omega dt. Yes, you have to add k times p sub k. But as I assume the symmetric part is just constant, that cancels out, and you are left with k sub times v sub k's to add, right? And I will call this function phi tau x omega, of course. And I will call this function phi of tau x omega. So phi omega, you see what the phi omega is. then it is the case that we write xt as xt minus integral from 0 to t. Mind that this is exactly the conditional expectation, conditional speed. So if I subtract phi eta s ds, then this is a martingale, as I said, but I have to add from 0 to t phi eta s ds. So we are back to the problem I considered. This is a martingale well understood. This is my problem. Right? So we are back there. Now, the theorem will hold not in full not without more conditions. The condition to impose will be the following, will be a condition on the correlations of this field. And that's my last word today. That's my last word today. So denote by C x ij. By the way, these are vectors. These are in RD. These are in RD. These have components. K is a vector. K is a vector. So RD. So that's why I put here ij. Right? Let C sub k be integral of phi I omega phi j tau x omega d pi. So that's the covariance of the drift field at the origin with the drift field at the side. And there is translation invariance. So, and denote its Fourier transform. This P is for Fourier transform. It's not for. So that's sum over x in zd ofCijx e to the I times p times x scalar product, where p is in minus pi to the d. This is the Fourier transform of a lattice field, right? And there is an extra condition. There is this h minus 1, very famous h minus 1 condition, which I state, and then I'm done for today. The h minus 1 condition is the following. That the integral on the cube minus pi to the d of trace of, say, sum over I psi I p divided by essentially p squared. So sum over I 1 minus cosine of pi. This is essentially the small p's matter. dp. This be finite. This is an infrared bound on the correlations of the drift field. You will see next time that this is equivalent to what I called h minus 1 before. Just it's in terms of correlations and infrared. Mind, this is green function. Correlations integrated against the green function, the lattice green function. So this means the following. The only singularity can come from p equals 0. At p equals 0, this is 1 over p squared. So the point is that c hat p divided by p squared be integrable at 0. Mind, due to Bochner or whatever, this is positive. So there is no sign problem here. This is a positive object. And b divided by p squared be integrable. This is something you can't translate back in the real space in a very easy way. Right? Stop for today. I overran about 3 minutes, which I apologize for. But we are done with the abstract, let me say, and we will see very concrete operators, very concrete things from now on. If you have any